Very good morning, students. Hope you all are doing good and safe. We had studied before lockdown all initial concepts and basic concepts of linear programming problem in classroom teaching, starting from definition of LPP, general and matrix form of LPP, formulation of LPP with sufficient number of problem solving. And moreover, you have worked out last week and last but 1 week in the name of home assignments several formulation of LPP problems too. Along with all these, we had even studied important definitions and terminologies of LPP like decision variables, objective function, solution, feasible solution, optimal solution to LPP. And we had stopped the chapter by specifying methods of solving LPP when nationwide lockdown was announced. Let's have a quick glance over what we had already studied in classroom teaching, and you can refer to your class notes either or textbook for those concepts what we had already completed in classroom. Let's start with linear programming problem definition. These all definitions and concepts, as I've mentioned already, we had discussed in length using several numerical problems also. Here we are trying to recollect all those before going for graphical method of solving linear programming problem. LPP is a problem of optimization. Optimization is nothing but either maximization or minimization of a linear function z. Z may be of profit, sales, cost, etc. subject to set of linear constraints. Linear programming problem is a problem of optimization, maximization or minimization. We had already studied this. LPP majorly deals with two viewpoints. One is manufacturer viewpoint and one more is consumer viewpoint. Any manufacturer who has manufactured his goods would certainly expect more or maximized profit based on his production. So if it is producer viewpoint, the problem deals with maximization, and if we are thinking about on consumer viewpoint, then any consumer would expect very much minimum possible investment in his purchasings. Of course, there is no compromise with the quality of the products. The same quality of the products, if he is able to get with a minimized cost, then certainly he would prefer. So that when we are thinking on consumer ground, it takes the dimension of minimization. So it is an optimization, maximization or minimization of a linear function z. That z is either profit, sales, cost, etc. Profit and sales, if we are thinking about, it is based on manufacturer viewpoint. Cost is nothing but based on consumer viewpoint. Subject to set of linear constraints we are specifying here. It is optimization subject to a set of linear constraints or conditions. Many more conditions will be there, many more real world problems will be there, many more constraints may be present while getting either maximization of profit or minimization of the investment. So we had already studied all these using some numerical examples, so I will not go so deeply in explanation. Let's again discuss all these concepts when we are solving graphical representation of LPP, if at all it is needed. Next, some more important definitions we had come across. Among them, the first one was decision variables. The variables x1, x2, so on up to xn, whose values are to be determined, are called as decision variables. Using any method, either graphical method or simplex method, whenever we are solving for solution of linear programming problem as an answer, then we will be ending up with values of decision variables. Whatever we will be defining initially, the decision variables, those values identification, those values computing, those values calculating or determining those values would occur at the end step of solving linear programming problem. That's why we are defining these decision variables to be the variables x1 up to xn whose values are to be determined or calculated are called as decision variables. Here it is given in n dimensional way, x1, x2, so on up to xn, but as we already know, in our syllabus it's restricted to only two decision variables, either it may be x1, x2 or x comma y. In our solved problems, if we have to recall what way decision variables defining has happened, one particular problem was given wherein a manufacturer is manufacturing two types of pens, type A and type B. It was somewhere rupees 8 was the profit based on type A pens each, and rupees 5 something based on each product of type B pen, what the profit manufacturer gets. In that case, an optimized values or an optimized value for manufacturer was to be obtained by solving linear programming problem. In fact, we have formulated already linear programming problem, solving that yet to be considered. So in that, just to recall, I am mentioning about it, we had mentioned let x be the number of pens of type A manufactured by manufacturer, and let x2 or let y be the number of type B pens manufactured. That way we had defined. Later anyhow, that only to be identified or that only to be calculated using graphical representation solving. At the end, after solving graphical representation, we will be coming across so many number of type A pen to be produced and so many type of type B pen to be produced in order to get optimized profit. So that here it is being mentioned the variables x1, x2, so on up to xn whose values are to be determined are called as decision variables. Next, cost or profit coefficients. Here also in both the dimensions it is given. Profit is nothing but on the basis of manufacturer viewpoint and cost is nothing but on the viewpoint of consumer basis. The coefficients C1, C2, so on up to Cn are called as cost or profit coefficients. Again here also it's n dimensional, so that C1 up to Cn it is given, and we will be restricting ourselves for C1 and C2 only in problem solving. But whenever definitions are asked, everywhere in n dimensional definition only we would be writing. One more definition, objective function. The linear function z, which is equal to c1x1 plus c2x2 plus so on up to cnxn, which is to be optimized, maximized or minimized, is called as the objective function of the general LPP. Here, what is this objective function is, as the name itself tells, objective. What is the major intention? What is the destiny? Or what is, like, our motto of solving this linear programming problem is being defined in objective function. This is what is the major objective of ours. What is the major objective in terms of manufacturer viewpoint? Total profit to be maximized. And what is the major objective or intention of consumer in his purchasings of several products, different products put together? Total investment or total cost incurred must be minimized. So that is being defined in objective function. This is a linear function just because we have mentioned total profit and a total investment. That's why, like, plus in between it will be mentioned. And what is C1 here? Cost associated with first product. What is X1? Number of type 1 products produced, if you are thinking in terms of manufacturer viewpoint. If you are thinking in terms of consumer viewpoint, what will be X1? It is the number of type A products purchased. Producer produced, consumer purchased, that way. If by chance cost associated with first product is 8 rupees and number of manufactured goods or purchased goods is 5, for example, 8 and 5, 8 multiplied by 5, totally it will be 40 rupees. And it is similarly second product maybe 7 rupees and 4 products, 7 multiplied by 4, 28 rupees, that way. So on up to all those n type of products either produced or purchased. So put together totally C1x1 plus C2x2 plus so on up to Cnxn will give you the total Z that is to be optimized, maximized if it is producer viewpoint, minimized if it is on the basis of consumer. So that will be called as an objective function of general LPP. Next definition is solution. We had already majorly concentrated on 3 such definitions: solution, feasible solution and optimal solution, which are very much essential and very important in problem solving using graphical method. Solution: a set of real values of x1, x2, so on up to xn which satisfy the constraints ax less than or equal to or greater than or equal to b is called as solution to general LPP. A set of real values in the sense these are all decision variables x1, x2, so on up to xn, which satisfy all the given conditions or all the given constraints, will be called as solution to general LPP. Next, feasible solution. Any solution to general LPP which satisfies the non-negativity restrictions is called as feasible solution to general LPP. We have started with the word any solution. Whenever we are telling solution, based on the previous definition, it is already satisfying all the given constraints. Then in addition, if it is satisfying non-negativity restriction also, it will be called as feasible solution. In the second definition of feasible solution, it is given point wise clearly. First point, that it has to satisfy it in the sense x1, x2, so on up to xn, the real values, has to satisfy all the constraints. And then in second point, non-negativity restriction also it has to satisfy. We have written here x comma y greater than or equal to 0 by thinking only two-dimensional decision variables. It can even be written as x1, x2, so on up to xn greater than or equal to 0 also, which will be called as a feasible solution to the general LPP. So put together, any feasible solution we are observing, it has to satisfy all the given constraints and also non-negativity restrictions. Then it will be called feasible solution. Next, optimal solution. A feasible solution which optimizes, minimizes or maximizes the objective function of a general LPP is called as an optimal solution to LPP. Here also again we may have to stress upon the first word of the definition, I mean feasible solution. Whenever we are specifying feasible solution, it's already satisfying all the given constraints and non-negativity restriction also. And then in addition, if it optimizes, either minimizing or maximizing the objective function, then it will be called as an optimal solution to LPP. In the second set of definition, it's clearly given stepwise that a set of real values of x1, x2, so on up to xn, which satisfy all the constraints, non-negativity restrictions, and then optimizing the objective function z equal to cx, will be called as an optimal solution to the LPP. We can write either in first way of definition or in second way of definition, whichever you find it to be easier, you can follow. Methods of solving LPP. Here only we had stopped in classroom. We had mentioned graphical method and simplex method are the two methods of solving an LPP. You might even remember second method was to be I had explained second method in this way. It's not simple method even or complex method. In fact, it is the combo of two, simplex method. Okay, anyways, you know already all the basic concepts of linear inequalities based on first PUC mathematics chapter. It was already discussed in classroom teaching also, that you have learnt already till placing of given inequalities in graphical form. Here we have to extend the same concept towards obtaining an optimal solution for a given LPP using graphical representation. We had already discussed finding out feasible region, that is, which satisfy all the given constraints or inequalities and satisfying even non-negativity restrictions also. The region which satisfy all constraints and non-negativity restrictions, certainly it has to fall in first quadrant because of non-negativity restriction. You are knowing about already two-dimensional axis, x-axis and y-axis, when it is plotted, four quadrants, first quadrant, second quadrant, third and fourth quadrant, how the variables signs will be present. In first quadrant, both the variables values will be positive, in second, third and fourth when you are going, either one of them or both values will go into negatives. So if it is to satisfy non-negativity restriction, which is nothing but positive values, it has to lie in first quadrant itself. So 1 mark usual question also may appear. Feasible region is always found in first quadrant. Why? In that case, your answer must be because to satisfy non-negativity restriction, feasible solution always lie in first quadrant. Sometimes it may be asked, in which quadrant feasible solution or feasible region always lies and why? In that case, your answer should be even it lies in first quadrant, and then the reason to be written as because to satisfy non-negativity restriction, it's lying in first quadrant. That's all. Okay. Well, let us concentrate on the methods of solving LPP now. As we have mentioned already, it is graphical method and simplex method. In our syllabus, only graphical method of solving LPP has been prescribed. But there may be a question appearing in exams to mention 2 methods of solving an LPP. So at least specification of second method as simplex method is prescribed in our syllabus. If that is the case, the question of methods of solving an LPP to be mentioned, we must remember even simplex method also to be mentioned. Now let us concentrate on graphical method procedure. You are already familiar with more than 60 to 70% of the procedure with the help of linear inequality chapter. Graphical method procedure. First and foremost, treat each inequality in the constraints as equality. For each equation, find 2 sets of points. As you have already studied in linear inequality chapter, the same procedure. All the linear inequalities which are given as constraints are to be considered with equality. For example, 2x plus 3y less than or equal to 4 if it is given. It has to be considered as 2x plus 3y equal to 4 first. And then by putting x equal to 0, what is the y value? By putting y equal to 0, what is the x value? Those are to be found out. That's what is given here. For each equation, find 2 sets of points. Not only for the first constraint, all the constraints are to be followed in the same procedure. By taking equalities first, it has to be calculated 2 sets of points. Then after calculating 2 sets of points, plot sets of points of each of the equations and join the points to obtain straight lines. It is nothing but the graphical representation we are speaking. 2 axes x and y either are x1 and x2, however that you have specified the decision variables, it's to be considered in terms of graphical representation 2 axes, and after that those calculated sets of points for each constraints may have to be plotted on the graph on both the axes and join those points using straight lines. Here we have to be cautioned in terms of separately set by set the points are to be plotted, and after plotting each set of points better to join as the straight line, and then one more set of values or set of points to be plotted on the graph. Otherwise we may get confused later while joining as straight lines. one set of point may be joined to another set of point later as the straight line, which will lead for wrong conclusions. So better first 2 points obtaining and plotting on the graph, and then joining as a straight line, and then again next constraints 2 set of points in the similar fashion to be plotted and then joined as the straight line. Then next, after joining them using straight lines, identify and shade the feasible region. What is feasible region? We know already feasible region always lies in first quadrant itself, and it has to satisfy all the constraints and even non-negativity restrictions. Mark the area or shade the area or the region which satisfy all the constraints and non-negativity restriction. In order to shade that, if in inequality given less than or equal to, from that straight line we may have to go towards the origin for shading, and if it is in case greater than or equal to, away from the origin, we have to consider the area or the region for shading as feasible region. This fact also is already known to you. Somehow I am stressing upon once again. After shading feasible region, identify the corner points of the feasible region and evaluate the objective function at each of the corner points. We have already shaded feasible region. The corner points of that feasible region may have to be written coordinate points, x and y coordinate points, or x1, x2 coordinate points, however that you have defined. And after that, our major intention was to find out optimal solution using objective function, either maximized profit or minimized investment in that case. So now all these corner points gives us either maximum values after putting in objective function or minimum possible values, so that these corner points are being used for such reason all those coordinate points to be evaluated using objective function, in the sense those coordinate points are to be substituted in objective function to get z value, and after putting in all those corner points values we will be able to get all z values from objective function. Then the corner point which gives the optimal value of the objective function is the optimal solution to the given LPP. In the sense, if we are solving for maximized problem, then among those few z values which we have already obtained using corner points of feasible region, which gives us the maximum value, that will be considered as optimal solution. If it is in case of minimized problem or minimization problem, which gives us minimum value, will be treated as optimal solution. Known fact, once again it is asked to remember, feasible solution to LPP lies always in the first quadrant due to non-negativity restriction of decision variables. This is being very important note. Once again it's asked to get remembered or get recollected. Some results, like results in the sense It's nothing but a final conclusion after solving linear programming problem and finding out optimal solution. What are the different kind of results that we will be able to interpret or give the analysis or conclusion of that analysis. First one, if an LPP has many, two or more optimal solutions, it's said to have multiple solutions. Two or more optimal solutions in the sense, in the previous slide we have already understood what way optimal solution is being found out. In case if it is maximized problem, then corner points evaluated value in objective function z will give different set of values. Their maximum, which is the value, that is nothing but optimal solution. If such maximum values are same in number 2 times or 3 times, for example, if 4 corner points are there, one is having 10 as the z value, and then next 20, 30, 40. Then if it is maximization problem, 40 is the maximum value among those, then the corner point which is responsible for the value of z is equal to 40 will be called as optimal solution with z equal to 40 as the value. If it is minimization, certainly 10 will be optimal value. We are speaking now about 2 or more optimal values. In the same answer, if it is in case 10, 20, 40 and 40 as 2 maximized values of objective function z. Maximum value we are finding out, so it is 40. It is appearing 2 times now. So it is said to have multiple solutions. Maximized values are 2 in number. In case if it is minimization problem, if the answers are 10 and 10, then 20 and 30. 10 and 10 are the minimum possible z values which we will be obtaining, and it is appearing 2 times. So again it is to be said multiple solutions. If an LPP has only one optimal solution, it is said to have unique solution. Quite easier one. Then if an LPP has no feasible solution at all, it is said to have no solution. Once when feasible solution is there, corner points will be used to evaluate the given z objective function and will be able to obtain optimal solution also, either in case of maximization or minimization. If by chance we are not able to get feasible solution only, then we will not be able to get further optimal solution. That's why if no feasible solution at all is present in a given problem, then it is said to have no solution. Usually such situation we will be finding out whenever 2 constraints are given. For example, one is less than or equal to kind and one more is greater than or equal to kind. Less than or equal to kind, we will be coming towards the origin, and for greater than or equal to kind, we will be going away from the origin. So common area which will satisfy all the constraints, given constraints, is not becoming possible. Such situations will be told as no feasible solution. Then certainly it would lead to no solution. Don't get confused with the definition of conceptual solution which we have learnt to this solution. This solution, no solution we are speaking about, there is no answer for the problem. That way the solution it is. Don't get confused with solution, feasible solution and optimal solution which we had studied. In that solution what we had defined is not or is nothing to do with the specification of no solution here. This no solution is no answer for the given LPP, that way. The next result, for some LPP the optimum value of z may be infinity. In this case the LPP is said to have unbounded solution when z increases indefinitely. This is nothing but after plotting the values, getting the straight lines between them, and getting the shaded area as feasible solution. If by chance all the constraints are greater than or equal to kind, we'll be going away from origin to have feasible solution. If all the constraints are greater than or equal to, when we are moving away from the origin, there will not be end at all later for that feasible region, because lower end we have already the corner points and end points. Since they are greater than or equal to all those constraints, it's going away from the origin in that way infinitely. There is no boundary line for that. Such situation we are treating it to be unbounded feasible region. Again, here we may have to concentrate properly and very cautiously. If it is the case of maximization problem, then it would take the dimension of unbounded solution, because the greater value of z is increasing indefinitely. The corner points initially which are present for feasible region we are having, but when we are going away from the origin infinitely, we are unable to get a specific corner point which gives the end point at the highest level for feasible region. So that z value, even if we want to obtain also, it is not like identifiable, it is going infinitely increasing. But if it is in case of minimization problem, lower end of that feasible region at least we know, that means lower end points we are familiar with already, we are able to get. So those are to be evaluated, and minimum possible value of z objective function among those calculated values using corner points may have to be written as an optimal solution. So to be put in nutshell, if an unbounded feasible solution is present with us, if it is maximization, the answer is unbounded solution. If it is minimization, minimum possible, first initial possible corner points may have to be evaluated using z objective function, and minimum value among the calculated z values may have to be written as the optimal solution. Till this we had already studied in classroom teaching. Let's solve some problems based on graphical methods of solving linear programming problem, which will give you already what we have understood the concepts, clear-cut idea about all those concepts. In the next video we shall solve graphical method of solving LPP. Thank you so much.